All right, so this is May, June 19, variant 11, question number 21. Let's see. Which compound has the molecular formula C6H10O? So let's see this. They all have one oxygen, 1, 2, 3, 4, 5 carbons. And this is the sixth. This is a CH3. So you have C6. Let's count the hydrogen. This is making 2 bonds. The third and fourth would be a hydrogen. This is making 3 bonds. Fourth is a hydrogen. This is making 2 bonds. Third and fourth would be a hydrogen. This is making 2 bonds. Third and fourth would be a hydrogen. This is already making 4 bonds. So you have 6 carbons, 1, 2, 3, 4, 5, 6, 7, 10 hydrogen and 1 oxygen. Therefore, the answer is A. What is the structural formula of the major product when hydrogen bromide reacts with 2-methyl-butene? So let's make 2-methyl-butene. So this right here is butene, and this right here is 2-methyl-butene. Let's see, major product, according to Markovnikov's rule, if the hydrogen goes to the carbon, which already has more hydrogen, that will give you the major product. So you see this carbon has 1 hydrogen, this has none. So if H goes here, Br goes here, and this becomes a single bond, this becomes the major product. Let's see the structural formula. So can we write this as C with 2 CH3s? So that could be C, CH3 twice with a Br, and then a CH2, and then a CH3. Let's see what option is that. So that is B right here. CH3 twice, CH3 twice, attached to a C, attached to a C, a Br, a CH2, a CH2, a CH3, a CH3. The answer is B. 23. Which reaction most likely to involve the formation of positively charged intermediate? 1-bromopentane. 1-bromopentane is a primary halogenoalkane. And if you remember, this reacting with NaOH aqueous. So this is nucleophilic substitution. This had 2 mechanisms, SN1, SN2. Primary halogenoalkanes always undergo SN2 mechanism, which does not involve the formation of a carbocation. This does not form any positively charged intermediate, therefore they can't be the answer. 1-bromo-2,2-dimethylpropane. Again, 1-bromo-2,2-dimethylpropane would be, let's see, so you have 1-bromo, carbon 1 has a Br, 2,2-dimethyl, so that's 2,2-dimethylpropane. If you see, this is again a primary halogenoalkane, which will undergo SN2 mechanism. Can't be the answer. 1-bromo, 3-methylbutane, so that would be 1-bromo, 3-methylbutane, so 3-methyl, 1-bromo. Again, primary halogenoalkane cannot undergo SN1, it will undergo SN2. SN2 does not involve formation of a carbocation. The answer therefore is D. And let's see D. So D is 2-bromo, 2-methylbutane. So 2-bromo, 2-methylbutane. This is D. If you look at the carbon, it has 3 neighboring carbons. The carbon with a halogen has 1, 2, 3 neighboring carbons. So this is a tertiary halogenoalkane. And tertiary halogenoalkane will undergo SN1 mechanism. And SN1 involves the formation of a carbocation intermediate. 24. Which bonds are responsible for peak X and peak Y? Let's see. Y right here is a strong sharp peak at 1700 roughly. This corresponds to C double bond O. So peak Y is C double bond O. Answer can't be A, can't be C, because it corresponds to C double bond O. X right here is a strong, it's a sharp peak, not very broad, around 3000. At 3000 you had alcohol, but alcohol was relatively a broader peak. It didn't look as sharp as X. It was relatively broader. So it can't be OH, and therefore it will be the CH peak. The answer is B. because CH is also roughly at around 3100, 3300, somewhere around 3000 to 3300. You can look it up in the data booklet as well. So this is a strong, sharp peak of CH. Alcohol looks kind of like this. And acid is even broader. Acid is like this. And alcohol usually has a double peak, right? One for the OH and one for the CH. It usually looks like this. That's the alcohol peak. And acid is broad, the broad OH peak. This is for carboxylic acid. And this right here is CH. Doesn't look like OH or anything else. 25. Let's see. Now, right here you have ammonia reacting with this guy, and they're saying you get this structure and 2 HBr. So let's see. What is the name of compound X? 1,1-dibromo 2-propyl cyclopentane. So you have cyclopentane. So we have cyclic pentane. On carbon 1, you have dibromo. So you have 2 Brs. And then you have 2-propyl cyclopropane. So 2-propyl, so that's C3H7 here. So let's see now. Now, if you look here, they're reacting with ammonia. The reaction with ammonia is nucleophilic substitution. And what happens is, then in place of the Br, you get an ammonia, you get an NH3. Yes. And right here you have 2 Br, so they will react with and they will make 2 NH3s instead of Br. Like the Br will get substituted by NH3. If you look here, in here you have 2 HBRs being formed. So the Br is being removed. So how is it making HBr? It's probably taking the H from this to make HBr. Yes. And let's see now. So you've made NH3. So you will lose one H so that this becomes HBr. So you will be left with NH2 and this will become HBr. This will also become NH2 and you will make this HBr. So the HBr is flamed. Now, if you look at the structure right here, in this, you just have one H attached to the nitrogen. Do you see that's not possible here? Because with these guys, you have two hydrogens left. So even if you try to make a cyclic compound attaching the nitrogen, you can't get this because you have 2 hydrogens left here, 2 hydrogens left here. Can't be it. Not it. A can't be the answer. Then you have 1,2-dibromo. Let's see. 1,2 dibromo, 1,2-dibromo, 2-propyl. So on carbon 2, you have a propyl cyclopentane. So let's see. It's a cyclopentane. On carbon 1 and 2, you have a bromo. And then on carbon 2, you also have a C3H7. Now, again, this would become NH3. This would become NH3. In order to make HBr, this would become NH2, and this would be removed as HBr. This would become NH2, and this would be lost as HBr. Now, it's already cyclic. Yes. I mean, we can't really, it's already a cyclic compound, just like this. You don't need to make it any more cyclic. But again, you see, when you try to make it cyclic compound, you will not get this because you have 1 hydrogen attached here, but here you have 2. Can't be it. Let's see 1,4-dibromo-octane. So 1,4-dibromo-octane. Octane is 1, 2, 3, 4, 5, 6, 7, 8 carbons. On carbon 1, you have a bromo, and on carbon 4, you have a bromo. Yes? Let's see. 1,4-dibromo-octane. Now it's a straight chain compound. So you make this NH3, make this NH3. Now we try to basically make this a cyclic compound. And when we try to make it a cyclic compound, let's see, this will become HBr. So this will lose an H, yes, and this will become NH2, and this will become NH2, and we will try to make it this, and these will become 2 HBrs. Clear? Now, when we try to make it into a cyclic compound, so if you try to make it into a cyclic compound, right? So let's see, when we try to make it into a cyclic compound, you will have 1, 2, 3, 4 carbons in the cycle, in the ring. But we know in this structure we have 5 carbons in the ring. If we try to make it into a ring structure, let's say a ring structure of this, connected via nitrogens. So you see, you will have only 1, 2, 3, 4 carbons in the ring. And you will have how many carbons on the side chain? 1, 2, 3, 4. But we have how many on the side chain? 3. Therefore, this can't be the answer. Let's now see. Let's now see the last option. In the last option, we have, let's see. So you have 1, 5. So this is a Br. And then on 2, 3, 4, and 5, you have another Br. So this will become NH3. This will become NH3. And this will become NH2. This will become NH2. And they will lose the hydrogens to become HBRs. Yes. Now, if we try to make it into a ringed structure, how many carbons would the ring have? 1, 2, 3, 4, and 5. And that's exactly what you see here. When you make it into a cyclic compound, it has 5 carbons. And anyway, when you go from ringed to cyclic, you lose hydrogens. So you see, you have 5 carbons in cyclic, just like you have it here. And you have 3 carbons on the side chain. Do you see you have 3 carbons right here on the side chain? Therefore, the answer is D. All right. So you don't necessarily have to really attach the two ammonias. What you can do is, it can, because you just have 1 mole of ammonia right here. So let's say one of the Br is replaced as NH3. Yes, one of them is replaced as NH3. Now, this will be losing 2 hydrogens. Why? Because you need to remove 2 HBRs. You're removing this. And how will you remove this? When the Br of this is going to attach to the H of this. So 1 H is gone to make 1 HBr. And then the Br of this will take the other H from here and make another HBr. Yes. So basically you have removed 2 hydrogens from this NH3 to make 2 HBRs. One, so let me just put them separately. One of them goes with this, makes an HBr. One of them goes with this, makes an HBr, and you are left with NH. When you're left with NH, now if you try to make a cyclic, the cycle or the ring will have 5 carbons, yes, and the side chain will have 3, yes. Therefore, this is the most viable option, D. Question number 26. Structural isomerism and stereoisomerism should be considered when answering this question. Let's see. 3-methyl-hexane-3-ol. So let's make hexane-3-ol. So this is hex 3-methyl-hexane-3-ol. Right here we have this. It is undergoing a reaction with hot concentrated sulfuric acid. What is that reaction? That is dehydration of alcohols. So dehydration happens in the presence of concentrated sulfuric acid. In dehydration, the OH loses a neighboring H to make an alkene. So the double bond can come here. This is one possibility, and that is 1, 2, 3 carbons like this. This is one possibility. This is one possibility where a double bond comes between carbon 2 and 3. Other possibility is this H and this OH is lost and a double bond comes here. Let me put it in a different color, in gray. So that's the other possibility, which is C, double bond. So between the third and the fourth. And then you have the CH3 as it is. So this is the other possibility. What is the third possibility? Do you see the neighboring carbon of this OH is also this carbon? So it can lose this hydrogen and this OH. So this can be lost as well. And the double bond can come where? It can come here. So that's the third possibility. So that's C, 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 double bond CH2 now. And then you have a C, C, C. Yes? 1, 2, 3, 4, 5, 6. So this is the other possibility. So let's see now. They are saying consider structural and stereoisomers of the different types of alkenes that we can get. You see, they've told you that it's C7H14, and that is a general formula for alkene. So this right here is your alkene. Now, these are the alkenes. We've drawn them already. We got to take into account structural and stereoisomerism. So let's see. Right here, can this show cis trans, the first one? Can it show cis trans? Yes, because you have a H, CH3, both are different. CH3, C3, H7, both are different. So this exists as cis trans isomerism. So there are two isomers for this. Let's see this one. CH3, C2H5, both are different. H, C2H5, both are different. This also exists as cis trans. So this also has two options, two possibilities. This one will exist as just one isomer because this can't show cis trans, because this carbon has two hydrogens. So no cis trans. So this only exists as one isomer. So a total of 5 isomers are formed. Question number 27. Compound T undergoes reaction with acidified manganate. So that means it gets oxidized. And it also reacts with sodium. So that means it can be an alcohol. Yes, because alcohol reacts with sodium. Now, if it is alcohol and if it gets oxidized, that means which type of alcohol can it be? Primary and secondary, not tertiary alcohol because they don't oxidize. Let's see the options. Can it be D? No, because D is a ketone. Can it be C? No, because this is a tertiary alcohol. Can't be that. This is a ketone, can't be it. Can it be B? No, because this is aldehyde. Aldehydes will not react with sodium. The answer therefore is A. Do you see this right here is a secondary alcohol? So yes, it will react with sodium metal and it will also undergo oxidation. 28, let's see. So you have compound X treated with 2 reagents successfully forming compound Z. So you're using a mild oxidizing agent here. Can aldehydes oxidize? Yes. What is a mild oxidizing agent? Maybe dichromate. Yes, because manganate is strong. So since you're using dichromate is why alkene will not oxidize, because alkenes only oxidize in manganate. So they only oxidize with manganate. So that's why alkene does not oxidize here. So let's see what will oxidize. So we will have the alkene as it is. The ketone does not oxidize anyway. So this stays as it is. The aldehyde will become carboxylic acid. Now, this is added to Y. This is Y. Now to this, you're adding NaBH4. That's a reducing agent. Let's see what will happen. Can carboxylic acid reduce to primary alcohol? No. This can only reduce to primary alcohol in the presence of LiAlH4. So this will stay as it is. This CO2H stays as it is. This alkene stays as it is. The ketone will become alcohol. Which alcohol? Secondary alcohol on oxidation. So first thing, acid stays as it is. Can't be C, can't be B, because they're changing the acid. Acid will not change because acid only reduces in the presence of LiAlH4. Yes? So B and C are not your answers. Can't be D because they've removed the double bond. The double bond will not oxidize because that only oxidizes in the presence of KMnO4. Answer therefore is A. Do you see secondary alcohol right here on the ketone? So that is CHOH, CH3. Yes? And the acid stays as it is. 29. Which reagent can be used to distinguish between propanone, that is ketone, and alcohol? 2,4-DNPH. Yes, we can, because 2,4-DNPH reacts with ketone, not with alcohol. Not B, because bromine water is going to react with alkenes, not either of these. Pellings and toluenes, they only react with aldehydes. So these react with aldehydes. Bromine reacts with alkene. Which compound is chiral? Let's see, 1-chloro, 3-methyl butane. So you have 3-methyl, 1-chloro, 3-methyl butane. Let's see, is this chiral? Can this be chiral? No, because it has 2 hydrogens. Can this be chiral? No, because it has 2 CH3s. Therefore, this cannot be the answer. 2-chloro-2-methyl butane. So let's see, 2-chloro-2-methyl butane. So you have 2-chloro-2-methyl butane. This is not chiral. This can't be chiral because it has 2 CH3s. This is not chiral, not chiral. Can't be the answer. 2-chloro-3-methyl butane. Let's see. So you have 2-chloro-3-methyl butane. Can this be chiral? Yes, because it has a H, a Cl, a CH3, and all of this. They are all different. This is chiral. Can this be chiral? No, because it has 2 CH3s. The answer, however, is C, because you have 1 chiral center. 3-chloropentane, you can check that. 3-chloropentane would be this. Can't be chiral. Why? Because on this carbon, you have 2 C2H5s. Answer is C. 31. Atom of calcium 48. Calcium we know is otherwise 40-20, but this is 48-20. And this has a charge of 2+. So let's count the protons. You have 20 protons. You should have had 20 electrons, but 2+ means you lose 2, so that's 18. And 48 minus 20, that is 28 neutrons. So it has 20 protons, yes. 28 neutrons, yes. 22 electrons, no. The answer is therefore B. 4 elements, X, Y, Z, have the configuration as shown. Now, based on the configuration, can you find the elements? This has 6 electrons. That means this is carbon. This has 8 electrons, oxygen. 12 electrons, magnesium. 19 electrons, that is potassium. So now they're saying, which will have low boiling points? Boiling points below room temperature. So that means these must be simple covalent structures. Yes, they should not have ionic bonds. If they have ionic bonds, they will be high boiling points. All right. So simple covalent structures, perhaps. Let's see. WX2. What is W? Carbon. X is O, CO2. Can this have low boiling point? Yes, because it's a simple covalent structure. YX. What is YX? Y is Mg. X is O. Can't be simple molecular. This is a ionic lattice. And this will have high boiling point. Can't be the answer. If 1 is right, 2 is wrong, answer is always D. 3 will also not be correct. Z2. Z is K. K2. X is O. This is also ionic. Answer is D. Which statement about enthalpy change are correct? Atomization is always positive. Yes, that's true. Atomization is always positive because you make gaseous atoms from their constituent elements in their standard state under standard conditions. To make gaseous atoms, you always have to give energy. Carbon-carbon bond broken whenever the energy change is positive. Yes, bond energy is always positive. To break the bond, you always have to give energy. Enthalpy change of neutralization is exothermic. Yes, neutralization is always exothermic. The answer, therefore, is A. Question number 34. Vanadium and pepsin can act as catalysts. Vanadium is a metal, pepsin is an enzyme. Which statement is correct for both pepsin and vanadium? They can catalyze any reaction. No, that's not true because enzymes are specific. Pepsin will only act at a specific structure or compound. This is used for because enzymes are specific. They have specific active sites. They will only catalyze certain reactions. If 1 is wrong, answer is always C. Catalysts lower the activation energy. Yes, they are not used up when they are used as catalysts. True, because catalysts, they are not used up. They remain unchanged. Which oxides, when placed in cold water for 1 day, will react with water? Magnesium oxide. Will magnesium oxide react with water? Yes. When you add this to water, magnesium oxide will become magnesium hydroxide. Aluminum oxide, no, it will not, because it is a giant ionic lattice. It does not react with water. Silicon dioxide is a giant macromolecule, does not react with water. Therefore, the answer is D. A mixture of magnesium carbonate and magnesium nitrate is heated. What are your products? So magnesium carbonate, when you heat this, it will give magnesium oxide, carbon dioxide. Magnesium nitrate will give magnesium oxide, 2 moles of nitrogen dioxide, half a mole of O2. So you make carbon dioxide, yes. Nitrogen dioxide, yes. Oxygen, yes. All three gases, answer is A. Moving on to question number 37. Let's see. So 37, which statement of polyalkenes is correct? So polyalkenes are basically polymers. So let's see which statement is correct. Polymers are saturated compounds. Double bond becomes single bond. They do not react with bromine in dark. That is true because they do not have a carbon-carbon double bond anymore. Disposal of polyalkenes by combustion produces harmful products. Yes, they can give harmful products. Polyalkenes do not readily biodegrade. That is also true. The answer is therefore A. Compound Y reacts with alkaline aqueous iodine to form a yellow precipitate. This is iodoform reaction. It changes color of acidified dichromate solution. So that means it undergoes oxidation. So let's see which one will oxidize. Can it be, let's see option 1. This is a primary alcohol. This can oxidize. It can be correct. 2 is an aldehyde. Can be correct. 3 is wrong because this is a ketone. It cannot be correct. Ketones do not oxidize. Now let's check 2. If 2 is right, answer is B. If 2 is wrong, answer is D because we've already eliminated 3. Now let's check iodoform. For carbonyls to show iodoform, you must have a carbonyl carbon with a CH3 next to it. In this, do you see you have a CH3 with a C double bond OH? So yes, it will show positive iodoform. This is correct. This will also be correct. Therefore, the answer is B. Anyway, let's check the criteria for alcohols. For alcohols, the criteria of iodoform is carbon with the OH must have a CH3, must have a H. Do you see this carbon has a OH, it has a H, it has a CH3. Do you see it has all three things? Therefore, this will also show positive iodoform. 39. Carboxylic acids can be made by several different reactions. By hydrolysis of nitrile, you can make ethanoic acid. No, you will make propanoic acid because you have 3 carbons. 1 is wrong. If 1 is wrong, answer is always C. From this, you can make butanoic acid. Yes, do you see primary alcohol can oxidize to give acid? And this is 4-carbon acid. Oxidation of 3-carbon aldehyde will give propanoic acid. True. Carboxylic acid react with alcohol to produce esters. Carboxylic acid form 1 ester only with the molecular formula of this. What could be X? Ethanoic acid. So with ethanoic acid, you just have 2-carbon acid. This is only 1 isomer. Now to make an ester of 5 carbons, you will need a 3-carbon alcohol because you have a 2-carbon acid. So you need a 3-carbon alcohol. A 3-carbon alcohol can be propan 1-ol. It can also be propan 2-ol. So will you have just 1 ester? No. Ethanoic acid can react with propan 1-ol, giving you a 5-carbon ester. It can also react with propan 2-ol, giving you a 5-carbon ester. Therefore, this will not give you 1 ester. This is wrong. Answer will be C. Propanoic acid. Let's check propanoic acid. 3-carbon acid. Now you will need a 2-carbon alcohol. So a 2-carbon alcohol would be just ethanol because there are no isomers of ethanol. So do you see you will only have 1 ester? Propanoic acid and ethanol. Yes. Butanoic acid. So you have butanoic acid and now you will need 1-carbon alcohol. 1-carbon alcohol has no isomers, no other isomers. So this will be also just 1 ester. The answer is C.